is the eccentricity. So now we have done this. Probably I can give you the third note. So 1, 2, and how about the third one to make this complete? So this is a note 3. Note 3 again. Let me using the drawing here. So this is the orbit, and this is the main focus. So this is satellite. And in these illustrations, I want to take another coordinate systems. And in terms of, rather than using Cartesian, and why not I take the polar coordinate systems. So this is ER, the radial directions, and then vertical to the radial directions, this is the E theta, and this is our velocity V here, and this is our vectors R. Okay, so again from we have known the angular momentum is R cross V, and we know this one is constant. And right now, based upon the selected polar coordinate systems, we can see how can we do it. So here in this way, the R basically here, we can describe, sorry, my writing is so, R equal to basically is R times ER in the radial directions. And V from here we can see, and so say here we are taking, this is the theta is the angle we switch from any reference locations. Okay. So say if we were able to measure the theta of the satellites in terms of the tangential these locations, then here we have the V is R dot ER and plus R theta dot E theta. Okay, so that is the expressions of the velocities in the polar coordinate systems, and this one is from the dynamics. So we plug in here. So basically here we plug in. So therefore H we can find is R squared theta dot in the K directions and EK. ER theta and K is out of plane. Okay. So here we have this one and the magnitude. Therefore, H has a magnitude R squared theta dot. So this provides us another interpretation of the conservation of the angular momentum. And what is that one? So this one is constant. And what I mean, that means is this. Let me draw this one in a bigger way. Okay, so this is our main focus. So say this is our the reference location from where we measure the theta. Okay, so this area, basically locally, if we have a small theta, say d theta, so that this area we have is 1/2 times R squared d theta, what we know earlier. Okay, and so this one quantity, basically this is 1/2 of if you look at it, compared to this one, basically let me define this is a area A. Okay, the A representing is the area the satellite sweep between certain durations. Basically, this one you can compare this one carefully. This is the 2 times A dot, right? This quantity is 2 times of the A dot here. This one is constant. So which means the area, the rate of the area being swept by the motion of the satellite on its own orbit is constant. So basically this saying is our Kepler's third law, right? The one of the Kepler's law. So that is another interpretation we can see. So from here, if, yeah, whatever, okay. Then we done the specific angular momentum. And now I'm going to do the second one, eccentricity. So you might ask me, and where is the such a reference locations and people used to take to measure theta? Actually, theta is one of the orbital elements, and that is one element to track the relative position of the satellites on its own orbit. And these reference locations can be determined by eccentricity, or not to determine, can be defined based upon the eccentricity. So to get everything short, maybe I can define this one to you. So what is this? So say if we only focus on the satellites, and which means elliptic orbit. So this is the center of the Earth. Okay, so this is the center of the Earth. This is the satellites here. So here we have 2 extremal points. So if we connecting this the minor focus, so we have 2 extremal points, this and this. And this point is called the perigee or peripapat perigee. And this one is called the apogee. Apogee, that means the farthest the farthest point away from the main focus. This is just the closest point. So perigee. Usually, people take perigee as the reference location to measure the angle. Okay, we define the theta is based upon this one. And how we know the location of the perigee, that is aligned to the eccentricity vectors, and that is the one we're going to talk about here. So the second one we're going to talk about is the conservations of the eccentricity, and that is a vectors, okay? Eccentricity vectors. And by definition, this one is equal to, let me rewrite there, and 1 over mu, and that is V H minus mu over R vectors. That one should be constant. And here I want to show you how to do this one. So again, from our equations of orbit, and equation 1 here we have, and then let me rewrite a little bit. So that means R double dot equal to minus mu and 3 R. Okay. Or this one is d dt v vectors equal to minus mu over R. Derivation is not that important, but just kind of show you how we did it. And the learning, focus for you is to use the equations to do the calculations. Okay. And so for this one, let me call this is equations. And so now we simply, I using the whole equations and this whole equations, and we cross product with H, then we see what happens. Okay. So this whole equation cross product with H. So on the right hand, on the left hand side, the D. On the left hand side, dV, dt, and cross H equal to the right hand side minus mu over R cubed and R and cross H. Okay. So now I'm going to manipulate these terms here. So this term basically we can try is this R. H, what we have obtained is R cross V. So I simply introduce the definition of H here. Okay, so here we have three things, and I'm going to implement, provide a formula here. A cross B cross C, and we can check out from this one equation is A dot C B minus A dot B C. The result of the three things, these things should be a vector, which is equal to B vectors with a magnitude that determined by this, minus a C vector that has a magnitude determined by this. So we plug into that one into here. I'm going to expand this term with that equation. So this one is equal to minus mu over R cubed, and so this is ABC, and that is AC, so A dot C, so that is A dot C side. A dot C, and with the B vectors, minus A dot B with C vectors. Allow me to change my symbol of V and using this one because I feel my writing is so full, so that could be easier to distinguish the V. Okay? Okay, so that will be here. And how about for this term? Again, let me use different color for the kind of scratch calculations. For this one, we can try is this. So here we can use, say, the polar coordinate system R equal to ER, and we've done earlier, and V equal to R dot ER plus R theta dot E theta. So with the two terms, and then we can take the cross product of the two terms. So basically, this one. So therefore, R dot V, and this one equal to the two terms take the inner product to its. So basically equal to this one, okay? And then the calculation of this term, this one simply is R squared. Okay, so therefore, we arrange the whole things. This one will be equal to this. These are minus outside the term, so I put a minus in. So this term will be go to the first, so that will be mu R3. Again, minus with a minus positive R squared V vectors, and then minus go to here, so that will be minus R dot and R vectors. And now here they both have R, so we get one R out, so that the mu divided by, again, I divide the numerator and denominator by R, so that is R squared, and that is R V minus R dot R. And again, here we manipulate. This one, if you look at this carefully, this one actually is d dt. This one, okay? So eventually we got is this. Let me combine this term and then this one together. Sorry, my typo here. So this one, if you look at that one, that should be equal to mu. That's it. Okay. So we combine the two terms together. Then let me use this color here. So that one will become dt v cross h minus mu over r equal to 0. This one, you can see a time derivative of certain quantity equal to 0. So that also is a conservation. The whole thing is defined as the mu times E vector. Okay, so the whole terms is equal to the B vectors. The B vectors is in our textbook. Again, in our textbook, and they're using B vector to represent this one. And this term, B vector, can be related to eccentricity. E is our eccentricity vectors here. Okay, so here in this way, the E is defined by this term, and that one equal to this one. Sorry. Here is so boring. The E vector is actually, again, let me draw this one since you have your notes. So this is our orbit. And this is the line connecting to the two foci. For example, this is the Earth, and this is the center of the Earth. Okay, and E vectors align to these directions. Depends on the orientation. Sometimes E vectors is pointing to these directions. Sometimes opposite. I wouldn't guarantee, but for sure E vector is aligned into the connection of the perigee and apogee. Okay, so that's a note. So E vector is the E aligned to the orbital plane, and E vector is normal to H. H is the direction of the plane. Okay, good.